They can hear me now. Okay, good afternoon, everybody. Welcome to this live session on this NPTEL course on theory and practice of non-destructive testing. So, if you have any questions right now, you can type that, and I can see those questions and answer to you right now, live. So, whatever questions and doubts you have, please feel free to clarify it right now. Hello, Anil. Hello, Anil. Can you hear me? Can you please reply to that? Okay, let me know your question. What is the question about welding, entity of welding? Can you be a little more specific, Anil? See, Anil, if it is very specific to CMT, as I can see from your question, I would try and answer that, although it's bit off from whatever topics we have discussed so far in this particular course. But as I said, I'll try and answer that. So you have like a question with regard to IR thermography in CMT. IR or infrared thermography, as we know it, or commonly known as thermal imaging, that's also one of the entity techniques nowadays which are being used in several areas, particularly with regard to identifying certain defects inside the materials or inside joints or wets. Okay? So similar thing can be done with respect to CMT as well, particularly when you are building the layers through this technique. Particularly, let's say at the interface, if you want to see whether the metal transfer has happened properly or if the interface bonding is proper or not. So those kind of information can be obtained if you can image the cold transfer metal and try and analyze those thermograms, right? So as you might know, if there are areas where there is not proper bonding or there is some kind of opening and so on, then those will appear as hotspots, as we call it, because there will be some kind of accumulation of heat or the heat distribution from those areas where you expect a defect or where there is a defect, heat distribution from the defected area, from the defects that you have, will be lower compared to the rest of the material. And as a result, the heat would tend to accumulate in those areas. So those will appear as hotspot if you are using IR thermography as an NDT technique for CMT. Right? So like that, there are other aspects also which might be analyzed using infrared thermography technique. So right now I can see a question from Sanjay with regard to radiographic testing. I'll come back to Anil in a minute or so. Let me answer Sanjay right now. His question is with regard to radiographic testing, and he wanted to know if two or more than two metal strip are there layer by layer, then how is fill pattern and in which metal defect is present can be calculated, can be concluded. Okay. So Sanjay, to answer your question, the first thing that I wanted to tell you is that every metal will have its own absorption with regard to X-rays. And that again comes from the same basic equation that we all have studied. That is, I equals to I naught e to the power minus rho x or mu rho x, which can also be written as I equals to I naught e to the power minus m rho and x, where m is the mass absorption coefficient, rho is the density of the material, and x is the distance or thickness of the material. Okay. So since m and rho are different for different materials, as we all know, therefore, the absorption by every metal, if you have two, three different metals in a layered structure, as you're asking, then the absorption by those will also be different. So, as you can see from the equation that I mentioned, if the density is more, then the absorption will also be more, right? Which means that the intensity of the X-rays coming out from a more dense metal would be lower compared to that which is coming out from a less dense metal. Let's say you have lead, iron, and aluminium, these three metals together, layer by layer, like how we are asking. Then most dense here is lead, followed by iron, and then aluminium. Okay, so aluminium is least dense, and lead is most dense, right? So that means the absorption by lead will be highest, and absorption of X-rays by aluminium will be lowest, and iron will be in between, right? So how does that reflect in your radiographic film? As I said, the intensity coming out from lead will be lower since it is absorbing more. As a result, the lead contrast that you see on the radiographic film will be less darker, and the aluminium contrast that you see on the film will be the darkest, right? And iron would be in between. So these are the three layers that you would see on the radiographic film. The darkest would be aluminium, then you will have iron little less dark, and lead will be more brighter. Okay, so this is how you will be able to, first of all, distinguish that which metal is what in the radiograph. And then if you have any defect, that also will show up depending on what kind of defect it is, right? Whether it is a crack or inclusion or any other defect that you are expecting. Let's say in these three layers that you have, and if you are talking about the interfacial bonding between any two layers, so that will also show up like any other defect where your bonding is not good, right? So that might appear as black again. If it is between iron and lead, let's say in that particular layer, so if you see at the interface, it will be darker compared to both iron and lead. So it will be, if it is an opening, linear opening, kind of thing at the interface, then it will appear as a dark line over there right at the interface. Okay. So that's how you can also get some idea about the defects. And pattern-wise, as I said, this will be 3 layers having a different contrast depending on their density. Nitesh is having a question regarding NDT techniques, and he wanted to ask if there is any more NDT technique apart from whatever we have covered in this course. So in this course, we have actually covered most of the commonly used NDT methods, and these are the techniques which are more common and most of the time used. But there are other techniques also which are a little more advanced, and they are used on a case-to-case basis depending on the requirement. In case the conventional entity methods that we have talked about, if those techniques are not very suitable, then in those cases other entity methods, for example the infrared thermal imaging that I was talking about, that can be used. And then there is neutron-based NDT techniques where instead of X-ray radiation, you can also use neutrons and things like that. But again, that has to be based upon the need of the user, where they think that the conventional NDT methods cannot be used, or where they think that they need to use more advanced techniques apart from whatever conventional methods we have. Anil, I'll come back to you now. With regard to your question about IR thermography again, and your question is with regard to research scope in IR thermography, particularly with welding. And let me tell you, there is a huge scope of research in this particular area, especially with regard to welding. A lot of people are already doing their research using thermography to identify or to qualify defects, and then study welds and try and analyze weld properties and things like that based on the IR imaging which is done. And you can study certain different aspects in welds and things like that. In fact, this IR thermography can also be used for what you call as the monitoring of health or health monitoring of different structures, identifying defects in those kind of structures which are already loaded. Okay. And that can be done live. I mean, that can be done when the part of the structure is in already use. Like, for example, a turbine blade, if you want to characterize it and you want to know if there is any defect, because there are several layers in these kind of structures. There is honeycomb structure and so on. So if you want to know those kind of details, and if you want to know if there is any disbonding or any defects and things like that, which you cannot see from outside. So the thermal imaging can reveal those details to you in a thermogram, in a image, in a thermal image, which which can be studied to identify and understand defects, and as a whole to understand the structure as to how it is internally, and to understand the quality of the structure, and to understand the health of the structure. Nitesh has another question with regard to ultrasonic testing, and he wants to know if it is important to bring the probe against the component firmly in all kind of inspection in ultrasonic testing. See, Nitesh, the thing is, as long as you can expel the air between the part which is being tested and the probe, it is enough. So it's not necessary that you need to apply a lot of force or a lot of pressure on the probe. But as I said, you need to apply some amount, little amount of pressure so that the air which is in between the probe and the part surface that is completely excluded. And that is exactly the objective of applying a layer of couplant or some kind of oil or grease. Technically, we call that as a couplant. So you first apply the oil or a gel or some kind of grease, and over that we can move the probe, applying a little bit of force manually. And you should apply that much force only, which would allow the probe to move without any difficulty. So there is no need to actually firmly hold it against the part. You simply have to bring it close enough and touch the surface so that there is no air between the part surface and the surface of the probe. Right? That should be enough. By the way, am I audible to all of you? Can you hear me clearly? Can anybody answer, Anil or Nitesh? Can you hear me clearly? Okay, good. So if you have any other questions, I'll be happy to answer. I'll be here for some more time. Anil, if you want to inspect dissimilar metal joints, which you are mentioning, it is of course possible to do it, but if you have a material like stainless steel, you really have to be careful when you are using ultrasonics for this kind of NDT, non-destructive testing. If you are using ultrasonics and you have stainless steel, then particularly with regard to austenitic stainless steel, you should be careful because stainless steel absorbs a lot of ultrasonic waves. The sound wave absorption in stainless steel is quite high, particularly in welds and casts where the grain size is large. So in those kind of parts, the attenuation of sound waves or absorption of sound waves by stainless steel is quite high. So that is the only thing that you should keep in mind whenever you are using ultrasonics on stainless steel. Another thing is you need to calibrate beforehand in order to make sure that everything is in place. Okay. So if you do that, it should be possible to inspect these similar joints as well. Sanjay has a question about UT again, and he's asking, is it possible in UT to show defective image like sonography? You would have seen in the lectures in ultrasonic where we talked about three different scans, three different types of scans: A type, A scan, B scan, and C scan. So A scan is what we normally describe, what we normally see, where you see those heights of echoes or the amplitude of echoes against time. But C scan is something where you can recreate a plant type view or top view of the sample which is being inspected. And as you would have seen in the videos, that in order to do that, you need to do the scanning in a particular manner. So you have to start from one end, and then you have to go zigzag across the surface of the part. Okay. So if you can do that, you can create, as I said, a plant type view of the entire surface, and then when you collect all the signals or all the echoes after doing that particular type of scan in that particular pattern, when you reconstruct those signals, then you will be able to create an image like how you see in a sonograph, which we call as a C scan, right? So if you can have the means and ways to make a C scan, to do a C scan, and then record it, that recorded data can be analyzed to create that image, which can be seen as a sonograph. So that was Sanjay's question with regard to ultrasonic testing. Now Nitesh has a very good question on eddy current testing. I think, yeah, eddy current testing, the effect of magnetism on the lift of car. So if you have a magnetic material, how the lift of car is different compared to a non-magnetic material. That is what he's asking. And this is a very relevant question. I think we have discussed that in the videos also, but I would like to explain it again with regard to this question. So when you have a non-magnetic material and you see it on that impedance plane, as you bring the probe closer to the surface, you are drawing the eddy currents or induced currents are flowing into the sample, and as a result of which some amount of energy is drawn from the coil of the probe into the sample, right? And that is why you see that the resistance of the coil is increased. So the lift-off curve comes down. That means along the x-axis it increases. That means the resistance of the coil increases and the inductance part decreases. So that is how you see the lift-off curve as a slant curve coming down from top and going down and towards higher R values, higher resistance values. Okay. So in this case, there is, apart from the magnetic field of the current which is flowing in the coil and the magnetic field that you have from the eddy current, there is no other magnetic field present, right? Now, if you have a ferromagnetic material, the material itself has its own magnetic permeability, right? So it will have its own magnetic field apart from the magnetic field that we know, which are present during eddy current testing. Apart from that, the magnetic field of the sample will also be present, simply because it's a magnetic material and it is being magnetized due to the current which is flowing. So, what this magnetic field of the sample will do is it will try and suppress the magnetic field of the eddy current. So, it will kind of mask the magnetic field which is in the sample, right? And as a result of that, the magnetic field or the induction component in the coil or in the probe, that would increase, right? So in the previous case where you have a non-magnetic material, we saw that the inductance of the coil is decreasing as you bring the probe close to the sample. That is what you normally see. But in this case, the magnetic permeability or the magnetic field of the sample would actually reinforce the magnetic field of the coil. And as a result of that, the inductance component or that reactance part of the coil would also increase apart from an increase in the resistance. So resistance would anyway increase because you are drawing some amount of energy for this eddy current to flow in the sample. So resistance would also increase, but in this case, your inductance part or the reactance would also increase along with the resistance. So that means the lift-off curve will not come down; it would rather go up. So it will be just opposite to a non-magnetic sample. So if you take it with respect to the null point, as we call it, that is when the probe is in the air, that is, it is away from the sample surface. So with regard to the air point, if you take it for a non-magnetic material, as you bring the probe close to the sample, the lift-off curve comes down. In case of a magnetic material, the lift-off curve will go up, sorry. It will go upward because, as I said, both resistance and the inductance will increase. Yeah, there is some mentions and or some questions with regard to TOFT technique. That's time of flight diffraction that we do using ultrasonics. And in many cases, it's a very useful technique, particularly when you want to do some kind of quantification, because most of the entity techniques are qualitative. But this ultrasonic method is one technique which also gives you some opportunities to also do it little more quantitatively, and TOFD technique comes in there, where you can use this to collect the echoes from tips of cracks, and with the help of that, you will be able to do some quantification. For example, identifying crack length or measuring crack length and things like that. So it's a useful technique in that sense. Practical demonstration of TOD, I'm not very sure how we can do it online, because it needs a particular type of setup that we need to create. It's more suitable for doing it in a lab setup, where you have all the things available. But I'll see if there is a possibility to create some kind of video which can be shared in the NPTEL portal. Anil, are you asking a general video for ultrasonic testing, or what is that? Yeah, if it is some kind of general video for the ultrasonic testing as to how it is done, that should be easy. We already have some videos, so probably I can share that in the NPTEL portal. Nitesh, if we have to create some NPTEL courses on advanced entity technique, I think that has to come as a different course. But of course, it is possible to create a course. But we need to identify, what kind of techniques should be of general interest to a larger crowd, right? So everybody might have their own specific requirements, but we need to identify techniques which would be having, more appeal to a larger section of people. So if we could identify those areas, those topics, then probably yes, we can create a course on other entity techniques also. Yes, Anil, you are right. Actually, there is an industry called PMET who are trying to develop these films, on page, the whole penetrant can be recorded, like how you do in case of that magnetic rubber which we discussed in magnetic particle testing, where the impression of the sample surface is created. So this is very similar to that, where the impression of the sample surface is created on a film, which can be attached or detached from the sample surface, and then you can inspect that film instead of inspecting the sample itself. So, but that is yet to be qualified for commercial applications. That's what they say right now. Sanjay, can you tell me the question for me? What is the question? I do not remember the question. I'll try and get it, but if we can repeat the question or write it here, then I can answer that. Assignment number 7, question number 5. What is that? If you could write it, I'll answer your question. So Nitesh, your question with regard to LPT, you are asking allowing some dry time for the part before developer application is needed. That anyway has to be there, because before you apply the developer, as you would have seen in the lectures, you need to clean the excess dye from the surface, right? So before you apply the developer, the surface has to go back to the initial condition, how it was exactly before you had applied the penetrant. So before applying the penetrant, we do a surface cleaning. The surface is completely cleaned. Similarly, before you apply the developer, the surface has to be cleaned again, and it should look like how it was in the beginning. So that is anyway there. It has to be clean and dry before you apply the developer. Maybe another 10 minutes. Okay, so Sanjay, I thought I have got your question. I think This is with regard to placing the intensifying screen, and you are probably asking how is it that the intensifying screen is both below and above? I mean, how is that particular option is the correct answer? See what happens when you keep the film, you keep it inside what you call as a cassette, right? Because the film cannot be exposed to light. If you expose the film to light, then it is gone. It will darken and you cannot record anything. On the other hand, you need to place that film in the X-ray machine. So anyway, you will have to take it out and take it to the X-ray machine to place it. So in order to prevent this exposure to light, visible light, normal light, what we do, we use a cassette and then load the film inside the cassette, inside the dark room, and then take it to the X-ray machine, right? So now this cassette has four walls, right? Or it has rather six walls, top, bottom, and the side walls. So there is a possibility that X-rays can get scattered from the bottom. That means from the floor of the cassette, right? And if these scattered X-rays, if they enter the film, then it might affect the quality of the image, right? So in order to ensure that these scattered X-rays do not enter the film, you may have to place some kind of intensifying screen at the bottom also, right? Apart from the top surface of the cassette, or apart from on top of the film, you may also have to have an intensifying screen below the film so that all these undesirable scattered X-rays are absorbed by that film. So the objective here is to absorb those scattered X-rays, the scattered radiation. What do you also call as the secondary radiation? So if you want to get rid of all those scattered radiation, then you may have to have an intensifying screen which will do this job, and that intensifying screen has to be kept below the sun. Nitesh, thanks for your compliment. I hope it was useful for you these 8 weeks of lectures, and hopefully, it will be useful for you in doing something practically. I also had a good time, teaching this course and recording it for all of you guys.
is correct. Okay.